Welcome to second lecture on terpenes and terpenoids. In this lecture, we are going to discuss about the chemistry of citral molecule. We will see the structure determinations, synthesis and reactions of citral. There are two isomers, citral and neral, which exist in cis and trans isomerism. We will see how these two can be differentiated on the basis of NMR spectroscopy. At the end, we will also discuss the NMR spectrum of the citral molecule. First of all, let us see from where we get a citral. The major source of citral molecule is from lemongrass. It is 65 to 85%. The second source of citral is lemon tea tree, and here 70 to 80% contents are present. The pleasant smell of the citral also contains in lemon. The pleasant smell of the lemon is due to the presence of citral, but its percentage is very less, it's only 2 to 5%. Now, because of the pleasant smell of the citral, it is used in aroma industry for making perfumes. It is also used as additives, food additives. It is also having medicinal property like antiseptic, antiviral as well as antibacterial. From synthetic point of view, citral is used as a starting material for the synthesis of vitamin A as well as a beta enone. Beta enone is having useful applications in perfume industry. Now let us see first of all the structure determination of citral. This structure determination of citral was carried out in the year 1890 to 1896. In those days, chemists were not having modern techniques for structure determinations. Therefore, they were relying on the chemical methods of analysis. The first stage for the structure determination starts from its isolations in a very pure form. Whatever the citral is isolated in pure form from the plant, then it is subjected to series of chemical reactions. The first experiment is the estimations of carbon and hydrogen. From the estimations of carbon and hydrogen, we reach to the molecular formula of the citral molecule, and it was found to be C10H16O. This molecular formula is a very useful information regarding the structure of a citral molecule. It contains 10 number of carbon atoms. It means that it belongs to a class of monoterpenoid molecule. When it is a monoterpenoid, we say it means there are two isoprene units joined through head to tail linkage according to isoprene rule. So we get a rough idea about the skeleton structures of citral molecule from the molecular formula. That is a 10 number of carbon atom. It means two isoprene units are joined together. The second information that we get about the citral molecule structure is from the degree of unsaturations or double bond equivalence. For a formula CXH5OJ, the double bond equivalence of a degree of unsaturation is equal to x plus 1 minus y by 2. So if you keep these values, the double bond equivalence or a degree of unsaturation is found to be 3. Now this 3 degree of unsaturation, it means that there may be a 3 double bonds, it may be 3 rings present in a citral molecule, or it may be the combinations of the double bond as well as triple bond. So in the subsequent investigations, we have to find out this nature of unsaturations. So towards this, the second experiment is to find out the nature of these unsaturations. So when this citral is subjected to hydrogenation, there is a formation of tetrahydrocitral, that is C10H20O molecule is formed. Then on bromination, citral tetrabromide is formed. Now if you do some chemical arithmetic, that is the molecular formula of the product, hydrogenation product minus the molecular formula of the citral, we see that two molecules of hydrogen are consumed by citral. Now since two molecules of hydrogen it has consumed, it means that the citral molecules contains two double bonds. In other words, out of 3 degree of unsaturations, we have now 2 degree of unsaturations due to the presence of double bonds. Now let us see the nature of oxygen. For nature of oxygens, two experiments have been performed. The first experiment is the reactions with the hydroxylamine hydrochloride or 2,4-dinitrophenylhydrazine. In case of citral, it is observed that it leads to form phenylhydrazone derivative or DNP derivative or the oxime derivative. So whenever aldehydes or a ketone is present in terpenoid molecule, then this kind of the experiments are routinely performed. If we get the oxime derivative or hydrazone derivative or a DNP derivative, it means that citral molecule contains carbonyl group. Now carbonyl can be aldehyde as well as a ketone. The nature of oxygen is proved to be carbonyl from this experiment, but it can be the aldehyde or a ketone. So the differentiation test, distinguishing test between aldehydes and ketones is performed using Tollens reagent. When citral is treated with silver oxide, that's a tolerance reagent, ammonical silver nitrate, then it leads to form a carboxylic acid with the same number of carbon atom. So the formations of a carboxylic acid with the same number of carbon atoms, it clearly indicates that this this nature of oxygen is in the form of aldehyde functional group. Similarly, citral molecule on reduction gives a primary alcohol called as a geraniol. So aldehyde also gives a primary alcohol. Therefore, it is confirmed from these two experiments that citral molecule contains CHO group as one of the functional group. So CHO group again corresponds to another unsaturations. In this way, we have proved the nature of 3 degree of unsaturation, that it contains the two double bonds and it contains one aldehyde functional group. And therefore, the molecular formula of citral molecule can be written as C9H15CHO. Now let us make some chemical arithmetic here. The hydrogenation product is tetrahydrocitral, and we have rewritten the structure of parent hydrocarbon of saturated product. Here is C9H19CHO. So corresponding to this, the parent hydrocarbon is C10H22, and this corresponds to CnH2n plus 2 formula, and therefore the citral molecule is a cyclic molecule. So in this way, we have reached to very useful information that citral is an acyclic molecule. It contains two carbon-carbon double bond and it contains one CHO group. Now let us see one more important evidence about the skeletal of citral molecule. When citral molecule was subjected to potassium hydrogen sulfate, then there is a formation of parasamine. At that time, the chemists were having very good data or very good literature about the aromatic compounds, and parasamine was usually formed in the dehydrogenation experiments by using potassium hydrogen sulfate or sulfur or selenium, leading to form parasamine. So formations of parasamine clearly indicates that citral molecule should have this kind of the skeleton where the methyl group and the isopropyl group are para to each other. So at this stage, we are having very useful informations about the structure of citral molecule. It's a acyclic molecule. There are two carbon-carbon double bonds, one CHO group, and it is a skeleton. Now in this skeleton, if we assign the positions of two carbon-carbon double bond as well as CHO group, then we can reach to the structure of citral molecule very easily. Now again, few more evidences for the nature of CHO group. When we record the UV visible spectrum of citral molecule, it is observed that citral shows lambda max at 238 nanometer. 238 nanometer is a clear-cut indication of alpha beta unsaturated aldehyde. Therefore, the CHO group, aldehyde group present in citral molecule is an alpha beta unsaturated aldehyde. Now the characteristics reactions of alpha beta unsaturated reaction is a retroaldol reactions. Citral on reactions with K2CO3 for a prolonged time leads to the formations of two carbonyl compound. One is acetaldehyde and methylheptanone. And the structure of methylheptanone was proved on the basis of ozonolysis experiment where it forms levulinic acid as well as acetone. So the formation of these two products, that's acetaldehyde as well as the methylheptanone, again proves that aldehyde is alpha beta unsaturated carbonic compound, and the formations of here acetone in the ozonolysis of methylheptanone clearly supports our this skeleton structure. So in this skeleton we have to keep one double bond here, and the another double bond is in the form of alpha beta unsaturated aldehyde. So on the basis of all these evidences, if we propose this structure of citral molecule, then one can understand this entire data of this chemical investigations. So this is a structure of citral molecule. We have reached to the structure of citral molecule where we see that there are two double bonds, and in support of that we have made a hydrogenation experiment, bromination experiment. Two molecules of bromine were consumed. CHO gives a test for tolerance reagent. It forms the oxide derivative, and here a retroaldol condensation can be understood. Aldol condensation can be understood in the form of this mechanism. First of all, hydration will occur. That's a beta hydroxycarbonyl compound called as a aldol, and then it forms here a retroaldol product, that is a methylheptanone and acetaldehyde. So in this way we have reached to the structure of citral molecule. Now this structure is again confirmed from oxidative degradation of citral. In the structure determinations of terpenes, normally the citral molecule is subjected to oxidations and it leads to form several products with a lesser number of carbon atoms. So these small molecules were known to the chemists at that time, and what are the products are formed in a degradation, depending upon that they were reaching to the structures of molecule under investigation. In case of citral, such oxidative degradation experiment was performed using KMnO4 and CrO3. So this KMnO4 and CrO3 oxidation, that's a vigorous conditions are employed here. So it's a levulinic acid is formed, acetone is once again formed, and oxalic acid is formed. So formations of acetone indicates here isopropylidiene group. Here formations of oxalic acid again proves here carbon-carbon double bond cleavage of this. One is a aldehyde already there, so it will form COH, and another will form COH here. So based upon this oxidative degradation experiment, we have now got some additional evidence about the structure of citral molecule as shown in 3. So let us see here how this we reach to the structure of citral molecule. First of all, we have calculated degree of unsaturations using the molecular formula, and then we have made the analysis of unsaturations by a hydrogenation experiment or a bromination experiment. These two experiment has proved that this contains two double bonds. Then it forms an oxime derivative. Therefore, the oxygen is in the form of a carbonyl group. Now, between aldehydes and a ketone, these two are distinguished with the help of Talens region. We got a gyranic acid. It means oxygen is in the form of aldehyde. Similar evidence coming from geraniol. Geraniol is a primary alcohol, so formations of primary alcohol again supports that oxygen is a aldehyde. Then KMnO4 oxidation gives you degradation product, and again here the positions of double bonds as well as the substitution pattern on the double bond can be proved on the basis of oxidative degradation experiment. Potassium hydrogen sulfate gives parathymine, and therefore it indicates the skeleton of methyl and the isopropyl which are proposed here para. So it is also confirmed. So on the basis of very preliminary experiments, chemists at that time reached to the very useful structure determinants of citral molecule. Now, once the structure is proved, we have to realize, we have to convince ourselves what are the actual products formed. We have seen that when it is treated with silver oxide, here we get a gyranic acid. The structure of gyranic acid is here like this. Same number of carbon atoms are here. If it is reduced with sodium amalgam, we get a primary alcohol. These were in the year 1890. Then in 1891, clue about the skeleton of citral was obtained on the basis of parathymine formations. Then in 1895, the positions of the double bonds, two double bonds, were proved on the basis of KMnO4 and CrO3 oxidation experiment. And oxidative degradation was also carried out in the year 1897, where we get a methylheptanone, and this on ozonolysis gives a levulinic acid. And the same levulinic acid is again obtained here also by the direct degradations of citral molecule under KMnO4 and the citral conditions. Now let us see here the synthesis of citral molecule. After structure determinations, we have to synthesize this molecule in a laboratory, and the synthesis of this molecule is a final proof for the structure of molecule. Now this is a structure of citral molecule, and its retrosynthetic analysis shown it can be prepared from methylheptanone. Methylheptanone is selected here because it was very easy to prepare this monosubstrate acetone molecule from ethyl acetoacetate chemistry. This is a allyl bromide. So ethyl acetoacetate is chemistry is employed in the synthesis of this citral molecule, and this 5 carbon atom, this allyl bromide, is obtained from acetone and acetylene. We get allyl bromide. So the reactions of allyl bromide with the base gives you alkylation product, and later on these two number of carbon atoms are introduced through Grignard reactions as well as the Reformatsky reactions. So if we know Grignard reactions, Reformatsky reactions, ethyl acetoacetate chemistry, alkynes in organic synthesis, Lindlar's reduction of alkynes, and the allylic rearrangement, these are the concepts. So if we are good at this concept, then one can understand the synthesis of this citral molecule very easily. In this case, the strategy, please try to understand here that acetone is here is a 3 number of carbon atom, here is a 2 number of carbon atom. These two joined together, we get a C5 unit. This ethyl acetoacetate provides 3 number of carbon atom, we get a C8, that is a methylheptanone. And later on the 2 number of carbon atoms are provided by Grignard reaction and Reformatsky reactions. to get the 10 number of carbon atoms. So the carbon-carbon bond forming reactions is involved here at one stage, second stage, and the third stage. There are three stages where the carbon-carbon bond forming reactions are involved, and the carbon-carbon bond forming reactions are mostly due to the ethyl acetoacetate chemistry alkynes as well as the Grignard reactions. So with this discussion, let us see how this actual synthesis occur. It was proposed in the year 1896. So synthesis starts from acetone, which is offering 3 number of carbon atom, acetylene 2 number of carbon atom. In presence of sodium in liquid ammonia, it forms propargyl tertiary alcohol. Propargyl tertiary alcohol undergo partial reductions to get a allylic tertiary alcohol, and allylic tertiary alcohol on reactions with the PBr3 forms here allyl bromide. Allyl bromide on reactions with it's an act as an alkylating agent. Ethyl acetoacetate in presence of sodium ethoxide forms an alkylating agent, alkylation product here, and this on hydrolysis with dilute NaOH from methyl heptanone. This methylheptanone can be assessed from acetylacetone as well as this dibromo compound derived from isoprene molecule. So we get here C alkylations here, and later on under basic conditions it undergo eliminations here as well as the carbon-carbon bond cleavage to get the methylheptanone. Once the methylheptanone is formed, there's a C8 number of carbon atom is formed here. We have to go for citral molecule synthesis, and here the 2 number of carbon atoms are offered from Reformatsky reactions. That's alpha ester. We get a beta hydroxy ester. Beta hydroxy ester on reactions with acetic anhydride form alpha beta unsaturated aldehyde. This on reactions with dilute KOH, it forms gyranic acid, and gyranic acid forms a calcium salt with calcium hydroxide, and if we heat this calcium salt, there is a liberation of calcium carbonate to form citral molecule. Now another same synthesis is using the Grignard reagent. Instead of Reformatsky reagent, we are employing here a Grignard reagent. We are getting here again nucleophilic addition across carbonyl, and we get a propargyl tertiary alcohol. Propargyl tertiary alcohol undergo partial reductions with Lindlar's catalyst, and this is a enol ether, and enol ether on hydrolysis gives aldehyde, and during this hydrolysis there is a simultaneously dehydration reactions occurring of this tertiary alcohol. This is a mechanism shown. Protonation will occur here, we'll get a carbocation, and then this is a allylic shift here, double bond will be shifted, and later on we will get here citral molecule. So both the syntheses are very old synthesis. It was the year 1896 when the first synthesis of citral was proposed. Then it is in the year 1948 it was used by using Grignard reagent after the discovery of the Grignard reagents. Now there is a modern method for the synthesis of citral molecule. It is also treated as an industrial method to prepare the citral molecule. Here these two compounds, allylic alcohol and this aldehyde, just they are heated in presence of an acid leads to form a citral just in a one pot. So methodology involved here involves sigmatropic reactions as a key step reactions. There are two reactions, one is a 3,3 Claisen rearrangement and another one is a 3,3 Cope rearrangement. Allylic alcohol in presence of an aldehyde forms a hemiacetal here. Hemiacetal undergo dehydration and we get a allyl vinyl ether. This allyl vinyl ether we can rewrite as in this fashion, and if this is heated it undergo 3,3 Claisen rearrangement, and we get here beta gamma unsaturated beta, this is a alpha beta gamma delta unsaturated aldehyde here. We can rewrite this structure in this fashion. Again here we find vinyl and allyl type of the moieties, and it is called as a Cope substrate. When this is heated it again undergo 3,3 sigmatropic rearrangement and we get this molecule, and this is molecule is actually the citral molecule if you rewrite in this fashion. So in this way, the industrial synthesis of citral can be accomplished with the help of sigmatropic reactions. Now let us see here. Citral molecule is very useful for the synthesis of other class of terpenoid molecule. For example, its reductions with sodium in amalgam, it forms geraniol. Its partial reductions gives citranilol, and its over reduction, that's another double bond, is reduced here. It forms citranilol. So citranilol, and geraniol, all of them are monoterpenoid molecules, and they can be prepared selectively by using citral. Another important applications of citral is found in perfume industry. Beta-enone is an important intermediate in the perfume industry, and it can be prepared by aldol condensation of citral molecule with acetone. So citral molecule on aldol condensation with acetone forms and followed by acid hydrolysis form two products, alpha-enone and the beta-enone. But the beta-enone is a tetrasubstrate alkene on this side. Therefore, this is a major product. Now the formations of beta-enone is a very interesting reaction and therefore it requires some discussion. The first step in the synthesis is aldol condensation with acetone. Citral reacts with acetone, we get a enolate anion, and this on reactions with the citral we get a beta hydroxycarbonic compound. This undergo dehydration to form alpha beta unsaturated ketone. So in this way one carbon carbon bond is formed. So the first step here is aldol condensation, and in the next step there is a cyclization reactions under acidic conditions. Under acidic condition there is a protonations of this trisubstrate double bond we get here, and then this carbocation is trapped here, we get a cyclization product. And this cyclization, this a tertiary carbocation has two options. It can remove the proton from this side leading to form conjugated system, or it can remove the proton from this side and it forms here alpha enone, and out of these two this is a beta enone is found to be the major product. Now this citral molecule exists shows cis trans isomerism. The cis form is called as a citral and the trans form is called as a citral and the cis form is called as a neral. This geranial and neral they cannot be differentiated on the basis of physical methods like boiling point. They are having very close boiling point, but with the help of NMR we can differentiate these two molecules very easily. This is a methyl group uh, attached to the double bond. This is a vinylic methyl group. This is also vinylic methyl group. Here in case of trans, there's a geraniol. This methyl group is deshielded due to the anisotropic effect of CHO. That's a carbonyl group. Whereas this anisotropic effect facility is not available with this methyl group. Therefore, this is shielded to some extent compared to this methyl group. And that's why this methyl group appears around 2.16, whereas this methyl group appears at 1.98. So this is a clue to differentiate between trans-citral and the cis-citral, that's a geraniol and the neral. If you make the reduction of these two molecules, then we get a geraniol, which is again a trans-allylic alcohol, and if we make the reductions, it's a cis-1, that's a nerol molecule. We will discuss about these two molecules in the geraniol chemistry. Now the last slide is related to the NMR data. At that time NMR was not available, but now the NMR data of the citral molecule is available. Here again this how many peaks are obtained. This is a 1, 2, 3, 4, 5, is a 6, 7 and 8. There are 8 number of signals are likely to occur, but some signals in the region here, this proton and this proton is likely to overlap because of the similar kind of environment. It is connected to the double bond, this also connected to double bond. But for remaining one, we get relatively clean data. This is appearing as a singlet. This 5.81, that's a olefinic proton, and this one is also olefinic proton. But this is appearing as a singlet, whereas this is appearing as a multiplet due to the coupling at these carbon atoms. And one can have here a long range coupling also. So multiplet is observed for olefinic protons, and these two this isopropylidine, these two methyl groups are distereotopic and they are not equivalent. It is appearing, it's a more deshielded signals because of the anisotropic effect. It is having more influence compared to this one. As far as the C13 NMR spectrum is concerned, we are having total 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 number of signal in a citral molecule. Entire molecule, there is no symmetry in this and therefore 10 signals are obtained. This carbonyl is observed at 191.28. Olefinic signals, there are 4 olefinic carbon atom 132, 122, 127. But this 163 we are getting again in a olefinic region, but it is very highly deshielded because of the minus R effect of the carbonyl group. This is methyl group appearing at 25.62, and these two methyl groups are distereotopic and they are not equivalent, therefore we get two different signals. So NMR spectrum of the citral molecule again proves the structure of what we have shown here. So in this way, we have learned the structure of citral molecule from the beginning. If we say we have started with a very simple experiment like hydrogenation, brominations, then oxime formations, parasamine formations, then oxidative degradations, retroaldol condensation, and with the help of that, we reach to the structure of citral molecule. Then in the latter portion, we have convinced ourselves what are the products actually formed in the reactions of citral. Then we have dealt with the synthesis of citral molecule using ethyl acetoacetate chemistry. Then sigmatropic applications of sigmatropic reaction is demonstrated in the industrial synthesis of citral molecule. And we have seen how this is a starting material for the synthesis of alpha enone, beta enone, geraniol. And NMR spectroscopy of citral molecule is also discussed here. So this is all about the chemistry of the citral. Now once this topic is prepared, the next part is about what are the probable structures or what is the question bank on this citral molecule. So there are various ways to ask the question. The students can be asked to write the products of the reactions when citral is subjected to ozonolysis reactions, retroaldol condensations, and the potassium hydrogen sulfate. So these three reactions are very important, and therefore students can be asked to draw the products of the reactions of citral. Another variety of the problem, I like to call this as a word problem. Just like in mathematics there is a word problem, here this is to some extent some descriptive paragraph is given, and out of that we have to find out the structure of terpinate. Here every statement leads to gives us some informations about the structure of a citral molecule, hydroxylamine reactions, molecular formula, tolerance reagent, then oxidation, the UV spectrum. So out of each argument or each informations, we have to just draw a conclusion, and this conclusion collectively we have to combine, and in that case we reach to the structure of terpinate X. This is X is nothing but here a citral, but one should try to understand here the quality of the problem or a variety of the problem. Next category of the problem likely to be asked is about the synthesis of citral. Instead of asking the write the synthesis of citral, the student should be given a chance to given some. They should be given clue in terms of the molecular formula of the intermediates involved here. Only they have to fill in the blanks in this entire scheme. Or alternatively, the reagents can be given, and they will be asked to arrange these reagents in a proper sequence for the synthesis of the citral molecule. The same thing is applicable here, and the last one here is about the mechanism of this beta enone formation, because here very basic reactions are involved and the students should know about it. That's aldol condensation and the carbocation reactions involved in the acid catalyzed cyclation to form the beta enone molecule. So this is all about the citral molecule, and we have completed the two lectures, introduction to the terpenes, second lecture is on citral, and now the third lecture we will talk about the geraniol molecule. Thank you very much for watching the video.